Okay, for number 14, I would consider simplifying the top as this, right? Hopefully you guys consider doing that. Does that make sense? Yeah, I did. I signed 14, didn't I? Yeah, see? Yeah, try this up. All right, and limit as x approaches 1. Then I'm going to rewrite it as a piecewise function. I could say x minus 1, x plus 1 over x minus 1. But that's true when x is what? Good, because you guys are getting it. And the other case would be the negative counterpart of the absolute value, which would be 1 minus x. I mean, I could put negative out in front, but I think you guys get the idea. If I put the negative out in front, it makes it 1 minus x. Do you guys see that change? And that's true when x is what? Good, because it guarantees you still get a positive denominator, right? Yes, so we're going to do that next. Let's just do one step at a time. So these cancel, so that's just x plus 1. And these cancel, we leave by a negative 1, so it becomes negative x minus 1. Okay, so as x approaches 1, the problem, well, first of all, does the limit exist? Because what's your right hand limit? And your left hand limit is good. Good. You guys getting it. Perfect. Awesome. Yeah, if x approaches 1 from the right side of f of x, I have to use the top function, which is, of course, 2, as you guys said. That's my RHL. My LHL is the limit as x approaches 1 from the left side, which, of course, is going to be negative 2. So first of all, did I rewrite the piecewise function? Yes, I did, over here. Did I find my left right hand limits? Yes, I did, in blue. Does it exist? No. And that's because the LHL does not equal to RHL. Okay, so that one seems like a pretty good test question. A very typical, like, hey, just do it, right? Or you do all these things for me. And so I think that's a pretty fair question. I didn't assign 15 or 16. I think those might be good for extra practice for you guys to do on your own. I'm gonna see if I can locate I know I have a bunch of files here. Let me see if I can find the answer keys. Otherwise, I'll have to kind of just use the weekend to work through it. I want to make sure you guys can check your work. But 15, 16, I didn't assign because that's just more practice for you guys. For 17, you have to rewrite that one as well. For 17, how would I do the rewrite? X minus what? Yeah, or the absolute value of right, because it's x minus 9 squared, but square root, they counteract each other. Because remember, this is factorable, like this. But you're square rooting it, so that gets us this. Because you have to guarantee a positive outcome. And then as a piecewise function, I could write like this. If I assume that x is larger than 9, you should get positive 9, because I just assume the absolute value just goes away, and I shoot that negative. Or if I assume x is less than 9, then I do a negative counterpart, which makes it 2x. Is it 2x plus 9? Yeah, minus 9. You're right. Yeah. Yeah, because you have to, right. So, yeah. And obviously, as x approaches infinity, that's 9. As x approaches negative infinity, that's going to be negative infinity because it's going down that way. And that does not exist. Yep. Mm-hmm. Okay, so actually, you know what? I should have done great question. Yeah, I should have put an equal sign somewhere. Whether I put the first or second is immaterial. But yes, I should have put an equal sign, or as a separate thing, I could put in fact equals 9 on its own. It's 9. This is continuous. Yeah, the problem is that I just forgot to do it. Yeah,
It's like in the denominator.
but sorry, the problem was right was in the denominator so that's how you could tell when you should. Yes, I should have put. I just forgot to do it for 17, but for 14, I was right to not include 1 because it'd be undefined. Yeah, so that's how you can tell. But yes, you should do that if you can. So that was just my forgetfulness, if you want to call it that. So. Yes. Yes.
Square to like the absolute value.
Well, that's just the thing that we defined. Whenever you square root a square, like square of x squared is not x. It's actually absolute of x. Because the fact that square roots have to always have positive y values, unless you put a negative in front of this radical, because to be a function has to have just one output. The square of x is like a half parabola, the top half of a sideways parabola, right? So you have to guarantee that. That's so like I'm sure you've probably seen maybe in middle school, like if you had like the square of x squared, they'd say, oh yeah, the answer is just x. But if you read the fine print, it'll say assume all variables are positive. They don't, they messed up because the proper way is to do this. Yeah, that's the reason why. Okay. And that enables us to then write a piecewise function afterwards and then do these limits. So, okay. Hopefully I feel we're good on that. This seems like there's a good understanding of how that works. Okay, cool. All right, good. Awesome. All right, these here, let's see if I can do this in my head. You guys tell me if I'm wrong. Question me, please. We did multiples of 3. Let's see here. That would be, so for part A and part B, part A, part B, part A, part B. It's gonna be 1 over e to the x, right? And so if x is approaching infinity, that should be 0. And if it's approaching negative infinity, it should be negative infinity, I think. Yeah, that should be negative infinity. Here, this should be 2 and -2. -2 for A.
Oh, I don't know why. Yeah, sorry, it shouldn't be.
Yeah. Yeah, let's explain. 1 over e to negative x is 1 over e to the x. So if x is approaching infinity, clearly that's going towards 0. That's pretty obvious. If you do negative infinity, then what's going to happen is if I go back to the way it was before, e to negative of negative infinity over negative infinity. So isn't that just e to the infinity? What's the top? That's the top. The top is large. Bottom's large too. But here's, and this is what we haven't really talked much about, but that's way more dominant than this. For example, e to the x. Sometimes you'll see this, like a double greater sign, because it means it's really, really that much bigger than x. This is true as x approaches infinity. Because if I plug in 100, e to 100 is way larger than 100, right? Significantly larger, e to the 100. So I expect a separation or a divergence between the numerator and denominator in terms of the values. But the fact remains, the bottom is still negative. So even though this is getting super infinite, that makes sense, it's still negative. That's why it's negative infinity. So that's how you can reason it without having to graph it or plug in a calculator. You can just sort of just think numerically what's happening. Does that make sense? How just to think like a mathematician, right? Think numbers, right? So that's how I kind of reason that one. But of course, you can verify with the calculator, not a problem. And by the way, our test will be graph calculator allowed for the whole test. So graph calculator allowed for the whole test, just so you know. I'm printing the ones from last year. I'll give it to you later today. For 6, if x is going towards infinity, of course, it's going to be 2. But it's going towards negative infinity. Remember, we had to do the absolute value in the bottom. That's why it's -2. For this one, if you do the end behavior model, it's going to look like this. If you ignore the -3. Oh, sorry, actually, that was terrible what I just did. I meant to say this. Obviously, I have to square with that too. If you do the end behavior model, the -3 becomes negligible when x approaching positive negative infinity. So you ignore that. √2 gets pulled out. So if x is going towards positive infinity, I think you would get 1 over √2. If it's going to a negative infinity, you get -1 over √2. √2 is 1.414. So if you do 1 over that, I think it's like 0.7 something. So you should see like 0.7 or -0.7. for 12, that should just be 5 in each case. Yeah, 5. Both A and B. Okay, so that should be 12. Questions so far? We're good? Okay. And then for 15, we're at the home stretch here. For 15, yeah, let's do cosine x over x cubed minus 2x cubed over x cubed. Now I know what you're asking at, Clay. That's just gonna be 0 because the bottom just gets bigger than the top ever would. And that'll be -2. So it's -2 for each case.
So is there a way, like, I understand why it's 0, but like, is there not a way to show it analytically?
I did. That's best I could do. To break it off like this.
Okay, it's 0.
Yep. Yep. Uh, 18, yes, there's a way to do it analytically. Remember we talked about that? You got to multiply top and bottom by 1 over x squared. I mean, I know what the answer is. I know the answer is 3. But you have to kind of show that work. And there's more to show. Like you have to do 3 minus 1 over x plus 5 over x squared. All over 1 minus 4 over x squared. Still got to keep the limit notation until you've actually evaluated it. And when you evaluate, then you can just say, oh, 3 minus 0 plus 0 over 1 minus 0. 3 straight up. Okay, we're good on that one. All right, and the last bit, 21. Yeah, if we're going towards negative, I'm going to use the top function. That's going to be 1. If we're going towards positive, that's going to be 0, right? Yep. And of course, that does not exist. Right, because it's 2 different things. Oh, wait. Hold on. Sorry. I misread that. My bad. Sorry. I don't use A and B. That was dumb. Those are not left and right hand limits. My apologies. For C, if x is approaching 0, actually still going to be does not exist. And why do I say that? Yeah, what's your left hand limit for part C? 2. What's your right hand limit? Yeah, that. Yeah, I mean it's getting closer to infinity, right? So yeah, that's what. But still does not exist. I was not wrong.
The left hand limit's like a closed dot, and the right limit's an open. It's still no.
Well, it's just about approach. No, there's no open dot. So if you were to graph this, right, it would look like this. So 0 is included. So there's a dot there. You're right. And it has a I think it looks like this, if I'm not mistaken. No. Hold on. Is that right? Hold on. How would that? There's a vertical azimuth at 1, but we're not including that. I think it looks like this. Yeah, it does. Yeah. Yeah, I'm right. And then this one here. Yeah, that's how the graph looks. Yeah. And so therefore does not exist yet. Okay. All right, good. I think we're getting the homework. Let's move on to the notes. Okay.
Second.
There we go. Almost out. Big killer. All right. Okay. All right. Let's talk about squeeze theorem, guys. This is kind of a funny theorem, but once I go through it, hopefully it makes sense. It's something that if I don't cover for a few years, I kind of forget myself. So it doesn't seem terribly intuitive, but once you kind of see the visual, it makes sense. So let's say g of x is the bottom function. So I'll call this g of x right here. And I'll call h of x the top function. And I'll call f of x the middle function. Okay, and let's say you have some interval. I don't know. Let's say I'm going from like x sub 1 to x sub 2. That's a 2. Sorry about that. So say my interval is from x sub 1 x sub 2. Okay. And x is approaching c. Okay, whatever c is. Actually, that should be a c. I don't know if that's a letter A there. That's confusing. Yeah, I'm not sure why that's yeah, I'm not sure why there's that's weird. That seems strange to me. That thing should be a C. Yeah. But anyway, if you take a look at both these functions, it's clear that h of x is always higher than f of x, and g of x is always less than f of x and h of x. So f of x is right in the middle. So ultimately, if you have some x by c, and then those both those limits equal each other. So basically, when both of these are meeting up, so h and g meet up at this x by at c, going to meet up there. Whatever that limit is, you can assume the same limits. You can assume the same limit for f of x because it's in between the two. That's why it's called the squeeze theorem. You're squeezing that function in between the two. Correct. Then the limit of x approaches c of f of x is also L. It still seems like an abstract idea. Once I show you an example like number 14, a concrete example, you'll see why this makes sense, why we need to have this. This can be true if you're trying to evaluate modes of x approaches positive, you need to use this theorem. And I think we'll have an example of that on the next page. I don't know. But all it's really saying is that, hey, you got top function, you got bottom function, you got a function in the middle. Whatever the limits are for the top and bottom, when they meet, if they have the same limit at a certain x value, then you can assume the same thing for the one in between. It has to be, right? Because it's in between the two. That's what it's saying.
How do you prove it's like in between?
That's what we're gonna do right now. Let's look at example 14. Okay, so that's a really strange function. X of 4 times. So let h of x. Sorry, let f of x. My bad. Let f of x equal the function in question. Okay, we're okay with that so far, right? All right. Also, we'll let so we're letting h be the higher function, right? And we'll let g of x be this. And let's assume our interval so these are all assumptions, just so you know. And I know you're probably gonna ask yourself, well, how do you know to assume those? Don't worry, it'll be clear. Just be patient. Those are all assumptions, though. Okay. So let's think graphically what's happening, right? X of actually we'll go to Desmos. Desmos is great. Okay, let's go to Desmos. So y equal x to the 4 power. Y equals sine of 1 over x. Okay, well, it's crazy, right? Y equals x to the 4 power times sine of 1 over x. Yeah, it's a little hard to see what's happening. But which one's green? Okay, green's in the middle. Okay. Yeah, hold on. Something seems really fishy at this one. Okay. Well, I don't know, things do seem a little off right now, but give me a sec here. There we go. Okay. Okay, so actually, I'm not sure if that was the proper one to use. Give me 1 sec here. Because as x approaches 0. Shit, okay, this is where I have to pull up my fold out notes. Give me 1 sec here. I'm a little stuck. I don't think I should have assumed g of x was that, because I can't find, because it's an oscillating.
Well, how else would you get that sign with 1/x?
Hold on. Oh, okay. I got it. All right. I know I did wrong. Okay, my apologies. Let's do this. I got you guys. I was wrong in doing that. That was my fault. Told you I was a little rusty with it. So I'm being very honest with you guys. Okay, we should have done negative x to the 4. My bad. Yeah, negative x to the 4. Yep. Okay. So one small change. Here's the reason why. Okay, now I feel better about this. Sorry for a little colorblind, but notice how the red curve is the highest curve, right? That's why I let x to the 4 be. The blue curve is the lower curve. That's why I let negative x to the 4 be. And of course, in between is that, right? And this has to work because if you think about it, if you're multiplying, so this is where you have to kind of think numerically what's happening. Hold on. If you plug in, like, say, 1, right? So that's it. Well, so let's say I plug in 2. If I plug in 2, that'd be 16. Plug in 2, what would that be? That's 16. Okay. If I plug in 2 to this, that's 16 times what?
Sign 1.
Sine of something, right? Can sine ever hold a value larger than 1? Never, right? Sine of anything can never be more than 1. So guaranteed, I know this can never exceed x to the 4 pound. And I also know it's never going to be less than this, because what's the lowest thing? Or even lower than 0. Negative 1, exactly. So can this ever be lower than negative x to the 4? No. That's why I know that this function has to be squeezed. So it's called squeezing. This has to be squeezed in between these two, because of the fact that sine has a range from what to what. Does that make sense? So if you consider the range of sine, that's why these assumptions work the way they do. So what I would do to help with your assumptions, figure out what this range is, and then figure out what functions you should have higher or lower. That would help you out.
So what is all this information in what direction to this?
So then what you do is this. Now I'm almost done. I got it. So now you do the limit as x approaches 0 of h of x. What's that going to be? 0. What's the limit as x approaches 0 of g of x? 0. So then you can make your statement. By the squeeze theorem, the limit of f of x as x approaches since f of x is in between there you go. That's your squeeze theorem. So it's like IVT. Remember that? Make some assumptions, make a statement. And of course, you do a little work right here. That's not much work. It's easy. But anyway, go ahead.
We also, the communication or the full like on the internet, so we have GRS and insurance. Or will we get a revision?
No, you're doing the quiz FX. I'm asking you this. That's the question itself. I have to do that, obviously.
For like defining what HX is and
G of x.
HX is.
Yes. Yes. Yes, always. Because you have to one higher, one lower. Yep. That's why it works the way it does. Wrong, go ahead.
The interval and like the.
Not really. That was kind of dumb, actually. I don't know why I'd had that. I think it's just so you guys can see what's happening. Not really.
So is the way you see like
Hmm?
if G of X and H of X are like higher or lower than M of X, is that just graphically?
Yep. 100%. Yep. Yep. Yeah. And if I show you the filled out version, looks here's the. I think I have this uploaded to Schoology as well. Should be right here. There we go. Yep. So, because we know that's true. Sine 1 over x between a 1 and 1. Obviously, x can't equal 0, but that's okay. Because we're doing a limit. It's all about approach. And if we do those individual limits for x of 4 and negative x of 4, there you go. So we do have to make some sort of statement that fx is between those two. And then, of course, state the squeeze theorem. So let's try it one more time, and then I think we're good on that. Then we can move on to other stuff. Okay, so what I would do, it's the same kind of thing again. I'll give you a second. Hold on, let me just finish writing. But go ahead, yes.
So like, I don't, if you can just like see the limit graphically, then what's the point of this?
What if what if this was in a non-graphing version of AP
How
exam?
would you know that it's between?
Well, that's what I'm doing right now.
And you
Uh,
not,
Sure, yeah.
and you not see the limit graphically because it's oscillating.
True. That's true. I mean,
I thought that's the reason, because it says like node.
yeah, that's true. You can't see it. Yeah, that's true. I mean, but I think we kind of suspect that if x is approaching 0, because we're multiplying by 0, right? But I mean, I guess you could, but it is doing some weird stuff with sine 1 over x. You're right, because it is oscillating. But I also do feel like, yeah, if you don't have the graph accessible, we need some sort of analytical way too, right? So, but you know, you are wrong. I mean, that's the reason why, because there is some oscillating at 0 for sine 1 over x. So we have that. Then we could say the limits as x approaches 0 of g of x is 0. The limit as x approaches 0 of h of x is also 0. So then you could say by the squeeze theorem, so I did one a little differently. I think this one's probably better way to do it. Just give me the assumptions for the functions, right? Tell me that this is true, that therefore this is true. This is true. So I can make that statement. So it kind of leads to all these things. So I have my assumptions. I have a statement about the range of sine 1 over x, which allows me to make this statement, which is the condition you need for the theorem to work. And that's also a true statement, right? Therefore, that must be true. If you show me that, you'll get full credit. You don't need to say more or less.
I
That's
just don't understand how you know it's between.
how I know it's between.
By seeing.
Because sine 1 over x is another component of this function that has a range from -1 to 1. So it's pretty clear that x cubed has to be bigger than this.
But like,
And negative x cubed has to be less, or they could equal each other.
Okay.
If sine happens to be at its extreme y values.
right, like I feel like there's gotta be at some point sine is greater than x cubed.
No, it's not.
Never.
No. No, think about it.
It can only ever be equal.
No, they could equal each other. They could do the same thing.
The sign never exceeds.
No,
Yeah.
but you're multiple. No. We're not comparing sine 1 over x cubed. I know what you're thinking. We're comparing x cubed times sine over x cubed.
Okay.
You're doing this. Yeah, I get what you're doing. You're comparing this versus this. I agree with you. There's times that could be bigger than this.
Right.
Like, for example, when x is negative, that could still be a positive outcome,
Yeah.
and that would be negative. No, we're comparing this. That's what we're comparing. When you have this, then it's pretty clear that it has to be this.
Okay, that's what you're saying.
That's what that's, yes, and we got that. Yeah, hopefully that cleared that. I'm glad we cleared up. Okay. And we're good. Yeah. No, because you want to guarantee that g of x is always less than this. So what's the lowest assigned? The lowest output, exactly. So you need to think of something that would always be less than or equal.
So it doesn't have to be X.
It's possibly in there.
I wouldn't change that. I would, because if you do x at 4 power, get yourself in trouble, because if you race into the 4 power becomes positive. I wouldn't do that. Actually, no, that would still be okay. If you put a negative out in front, actually, it wouldn't matter. That'd be fine. That wouldn't matter. And we got,
So it doesn't have to be like that. Okay, less than. So g of x doesn't have to be like something that's unemployment of x. It has to be like,
guarantee, yes, it has to be less, but it's easy if you use a component to make comparison easy.
oh, I see, okay.
It doesn't have to be. Sure, you could then negative x to 100 power. I don't care. You do whatever you want. But the things that you have to,
All you're guaranteeing is that it's like,
it's just easy to use some part of it and make it negative. If you think about the range of this. Yeah, I mean, I can put -2 in front, -2x cubed, I'm fine. Wouldn't matter. But you want to be careful because you want to make sure that you can get a limit. You want the same limit for both of these. That way you can use the squeeze term, that's why. Yeah. Really good.
Asked if, like, we were asking a limit to approaching somewhere where they weren't like spaced together. Where they were-
No, they will squeeze together, because I want you to, because I want this to be the same. 'Cause you can't do it otherwise, they have to be the same. That's the whole point, we want the squeeze term to work, we want to squeeze together. They're not gonna diverge, we don't want that. Well, it kind of, that was the case for the original for f of x. That's what we had to use the squeeze term, because I couldn't evaluate 0 straight up. Because there's a lot of weird stuff happening here. That's oscillating, right? So I needed some other method or means to show that. And that's how I'm showing that with this. So, okay, let's move on to the next part of the notes. There's just some odds and ends, just to wrap up here. We'll see how we do with this. Okay, so let's talk about extended functions. So let's graph this here. That's gonna be what? X minus 1 over root x minus 1. There we go. Okay. It's like I don't see it. Okay. What does that look like? That graph. Square of what? Y equals what? Root x. Yeah, because this could be written as a difference of squares. Even though x is not squared itself, isn't x the square of root x? Right? So you could write it as, yeah, you could write it as root x. Those cancel. So yeah, that's what we see there. Okay. So let's go back to the notes. Here we go. So when I graph it, pretty simple. It's pretty clear that I could start it here. However, there's a hole here. Why is there a hole there? Yeah, if I go back to Desmos again, if I kind of mouse over it, see it says undefined, right? because you can't divide by 0. So it's still undefined, so it's a hole in the graph. Yeah, it's a point discontinuity for sure. So you just kind of help you, blah, 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 where's undefined, obviously at x equals 1. We got that figured out. Algebraically determine it. I kind of did that for you already, but I'll do it again. That's how you can rewrite it. That's 1, not 0, duh. Remember, be formal, write the limit notation until you're ready to substitute. Now we're ready to substitute, you bet. I get 2. So using parts A and B, identify the type discontinuity. So it's definitely a removable discontinuity. And that's because well, really because F1 does not exist. But the limit as x approaches 1 does exist. Sorry, say again? Yes, yes. Also, f of 1 does not equal. Because f1 doesn't, did not exist in the first place, right? So when the limit exists, but there's not a point there, then the point got removed, right? That's why it's removable. Or it could be floating somewhere if you had a piecewise function. Maybe if I had a piecewise function involved this, great. Maybe the point somewhere else. But f1 does not equal that limit. That's also another reason why.
How does F1? Oh.
F1 will not be part of my domain. Right?
Like that last line isn't really show anything. 'Cause
So sometimes we might need to say that. Because what if I had a piecewise function where I did want one to be part of the domain? So what if I had that expression as part of a piecewise and then another part that said, yeah, at x equals 1, it's like 5 or 10. Then f1 would exist and the limit would exist, but they still equal each other. And that's why, again, the point's been removed. The jump happens when the limit does not exist. When the left right hand limits are like this, that's jump. When it's like this, but it points somewhere else, that's removal, right? And then this is kind of the new part. The extended function is that, let's say you want to be continuous. So you want to force the issue of continuity. Then you write it like this: f(ext), which stands for extended, of x equals x minus 1. This is true when x is greater than 0 and x does not equal 1. And we'll put 2 when x equals 1. So obviously x has to be greater than or equal to 0. We know that, right? And of course x does not equal 1. But when x equals 1, we do that. Yes, exactly. Good. Or good. Recommend reader. Or you can write like this. So you can write either or. The piecewise function is more formulaic or a recipe like, hey, just write the function itself, exclude what you got to exclude, and then fill in the hole in the second part. Or you can take the simplified form and say, hey, ignorance is bliss. I didn't even know there was an issue. I didn't even know there was a root x minus 1 in the first place. Just pretend you don't know. Plead the fifth. I don't know. If you want to call it that. Just say, here it is. Root x plus 1. Because root x plus 1 on its own, if I just told you, hey, root x plus 1, is it continuous at 1? It's like, well, of course it is. Yeah. No kidding. But we know that it came from something else. So we just have to call an extended function. Just to be honest and transparent about it, right? If that makes sense. Let's try it again. And again, don't overthink it. It's just really more just simplifying and filling the gap. That's what all you're really doing. So analytically determine this limit. Well, that's easy. You agree with that, right? We're cool with that? So how would I write your extended function? You can write like this. Just x minus 2 straight up. You don't have to write as a piecewise function if you don't want to. You can. I don't care. You can. But that would be the extended function. Because that's not truly what we have. What is this? That's just a line, right? That's a line also. It simplifies to a line. Well, the hole. You want to get rid of it? You want to fill in that hole? Go with this. That's why it's extended. You've extended the function to fill in that hole. That's why it's called that. So it's forced an issue of continuity. All right. So again, don't overthink it. Okay, let's press one more time then. Ooh, I love example 4. Anyone who knows me really well, who've taken my class, I absolutely love these problems. So it will be on a test, 100% it will be. The reason why I like it, because it really kind of covers a lot of topics into one question. That's why I love it so much. We'll get to example 4 in just a moment. And there's a really nice version of that when we get to derivatives and differentiability in the next unit. That kind of is similar to example 4. Great AP style problem. But let's look at example 3. Okay, you want to extend this. Is there a hole here? Yeah. So in this case, we have to kind of write like a piecewise function. So that's what I'm saying. Like sometimes we have no choice but to write as a piecewise to fill in the gap. Sometimes we have to do that. So you'll say this. And seriously, there's no work to show. You just write. Okay, this is the one thing. And actually, I remember in grad school, like we were like, wait, what work do we have to show? And press like, I told you to write. Just write. Done. That's it. Give it to me. Done. So there's no work to show. X is not equal 0. And then how do I fill in the gap? What do I write? Done. That's it. You feel like, well, I'm missing something. No, you're not missing anything. That's all I need. Just give it. So, because there's a holes there. Well, the limit. I know the limit as x approaches 0 of that function is 3. So it ties back to the limit, right? Because remember, for continuity, what do you need to have happen? Does f of 0 have to exist? Yes. Does the limit as x approaches 0 have to exist? Yes. And does f of x have to equal, or f of 0 have to equal that limit? Yes. So if you want to show some work, I suppose you could do all this stuff here. Because those are the 3 conditions of continuity. Right now, on its own, does f of 0 exist? Absolutely not. The limit exists, but the f of 0 does not exist. So how do I force that issue? Make it exist. Make it happen. And guess what? That limit exists, that's fine. And then do you want f of 0 to equal that limit? Yeah. So I didn't choose some random number. I didn't choose like 5 or 6. I had to choose 3. Because will 3 fill in that gap? You bet. So are all 3 of these things now satisfied as a result? Yes, they are. So that's really the overarching principle here, right? These 3 conditions must be met to make that extended, to fill in that gap. Okay. Just to kind of tie up the notes here. Let me just pull this up really fast here. So what is a continuous function? Well, I mean, it's many ways you could define it, but something that's continuous on its domain. So I mean, you could say no breaks in the graph or all these other things, I suppose, but essentially anything that is continuous on its domain. So one over x counts, logs count, exponential functions, trig, polynomials, properties. We know this is true. This is what I really wish I could get to this. I don't think it will. So I'm going to do this. So we have 75-minute periods next week. I am going to talk a little bit about composites next week because I do need to do that with you guys. And we'll be on the test, but we'll also use review on Wednesday as well, just so you know. Because we don't meet Tuesday next week and no school Monday because you guys have a day off. I have to be here and work. Good for you guys. Bad for me. No, it's good for me. But it's a weird 4-day week. So on Wednesday, we'll have 75-minute class. I'll talk about this, like what happens with limits with composite functions, because that's kind of a weird thing. It's not hard, but I'll talk about it with you guys, and then we'll do a review as well. Let me wrap this up just so we kind of close the loop here on this stuff. IVT, I'm not going to talk about because I've already assessed IVT. In fact, actually, I've decided I'm not going to put IVT in our test because I've already assessed that with you guys. I don't need to do it again. So even though it's here, I'm going to forego that. So IVT won't be on our test, just so you know. Okay. So let's just wrap this up here, and then we're done for today. And I told you I really like this kind of problem. Okay. So this is an AP style problem. I want this to be continuous, right? Okay, the quick and easy way, I'm going to show you both ways. Quick and easy way is just so you know you got the answer, but you won't get full credit because you will not get full credit in the AP exam. And then I'm going to show you the formal way. So we'll do a quick and easy. It's kind of like if you have to make like instant oatmeal or instant rice in the microwave. But if you want to, cook a good meal the right way, take the time. There's the formal way. Okay, quick and easy is this. And solve for a. Plug in 2 for x. Because they have to link up, right? Otherwise, they're not being continuous. They have to link up. So you get 3 equals -4 plus a. What's a going to equal? See, there we go. Okay, that's easy. Okay, if this were a multiple choice question, I would encourage you to do it this way. I encourage you this way because they don't look at your work. Multiple choice, go for it. Give me the answer. Formally, here's what you got to do. You have to go through all the steps of continuity. Or all the conditions. The first condition. What's the first condition? F of 2 must exist, right? Well, does it? What's F of 2? Okay. Good. Condition 2. What's that condition going to be?
What's it?
Yep, limit as x approaches 2. So if I do the left-hand limit, what's that going to be? What's my right-hand limit? Well, not yet. We don't know just yet, right? -4 plus a, right? Now, for the limit to exist, you have to work out the left hand limits. You have to work it out. And then you have to make a statement that if I want the limit to exist, I need to eliminate the RHM. So make it work.
make LHL equal RHL and solve it. Did I make the LHL equal to RHL here? Sure. But I didn't write all the formalities of limit notation. I didn't use those conditions of continuity, I just did it quick and easy and I got 7. But that's what you have to show.
And the third condition is this over here. Then you have to make sure that f of 2 equals that's just a final confirmation. That's more of a sanity check than anything else. Yeah, exactly. So 3 equals 3, yes. You don't really have to show that.
It's this we have to show.
That's how it's done. Okay, let me go
Grab the whole test. Last year's gonna have off of that.
They beat you at like 2 years ago, right?
Yeah, kind of the answer piece, but that didn't come out, so at least it has something, that's good. So this stuff from last year, hopes that you guys can take a look at it. Yeah, we can work out some class tomorrow. If no one's interested in doing SAT style stuff. But I'm gonna talk about and bring a device tomorrow. And you may want to download the Blue Book app as well. And I'm gonna have you guys go through a practice test with me.
Oh, we have the test right now. Oh, yeah, that's good. Yes. This is. I mean, we can do it to be better on him. That's good.
He just remembers all the answers. It takes him 2 minutes, then we got to do I'll talk right now. I appreciate that.